This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
Good evening and welcome. My name is Nigella Hilgarth and I'm the Executive Director of the Birch Aquarium at Scripps Institution of Oceanography at UC San Diego. I'm delighted to welcome you to the most recent Jeffrey B. Graham Perspectives on Ocean Science lecture tonight. And it is my pleasure to welcome tonight's speaker, Dr. Jeffrey Severinghaus. Now, Jeff is a professor of geoscience here at Scripps Institution of Oceanography. He received his PhD from Columbia University's Lamont Doherty Earth Observatory in 1995 in isotope geochemistry. So it won't surprise you to learn that he is an environmental geochemist. And he works on gases that are trapped in ice cores. And so by doing that, he can reconstruct past variations in atmospheric composition and climate. And his research takes him to some of the coolest parts of the world, literally. He goes to Antarctica and Greenland and has participated in lots of exciting partnerships to retrieve ice cores from those areas. And so I'm delighted to welcome this very distinguished scientist at Scripps to his lecture tonight. So please join me in welcoming Jeff.
Thank you, Nigella. Paul, it's a great pleasure to be here this evening. And my goal is to try to tell you about some of the things that we might learn about our future by studying our past. And in particular, my interest is in the ice, the great ice sheets on Greenland and Antarctica in particular, because those bodies of ice, it turns out, contain little air bubbles that trap secrets about our past, about past climate and atmospheric composition. And so I hope to give you some updates about things that we have learned, we scientists have learned in the last few years. And I always like to start out my lectures with a picture of the next generation, because it's really all about the next generation. I see the climate impacts that we're going to experience as rather mild, and that the really harsh impacts are probably going to be felt by our grandchildren. So in some sense, what we're really talking about here is acting or not acting on behalf of our grandchildren, or maybe two or three generations hence. But I just like to remind myself that to keep my eyes on the future. So, what can you learn from ice cores? Well, first, a bit about ice cores themselves. Ice cores are cylindrical pieces of ice. This is an example, and they are dated by counting annual layers, just like tree rings. And so we can get an accurate age of the past. And the reason why this works is that in the polar regions, it's so cold that the snow never melts. It just keeps piling up year after year after year, making an uninterrupted sequence of layers, each layer corresponding to 1 year. And it turns out that the reason why this doesn't just continually pile up until it reaches the moon is that ice is a viscous substance. Think of it as pancake batter on a griddle. It tends to flow under its own weight. So when it gets to about 2 miles thick, it just can't really get much thicker, and it starts to ooze out sideways, and eventually, if it's cold enough, it'll just break off and float away in the ocean as an iceberg. And so that's what happens mostly in Antarctica, actually. You don't get that much melting in Antarctica proper. Mostly the ice just breaks off and floats away as an iceberg. And of course it melts just fine once it's out in the open ocean. So this is what the air bubbles look like. So they're about 1 millimeter across, not very big. And as you can see, there's lots of air trapped in the ice. The reason is simple. The snowflakes, as they fall, have some air in between them, and as the snow is compressed into ice, it doesn't succeed in expelling all of the air. And so a little bit of air is left in between the snowflakes, and eventually that gives you ice with air bubbles in it. About 10% of the volume of ice is air bubbles. This is a cross-polarized photograph, so you can see some pretty colors here. This is an ice grain here, and this is another ice crystal, and then these black things are the bubbles. Again, about 1 millimeter across. And so what do we learn from the bubbles? Well, many of you will have seen this kind of figure. This is 400,000 years ago on the left, and time increases as you move towards the right. And here we are in the present. And so what you see on this graph are CO2 concentration measured in the bubbles. And as far as we know, this is an accurate representation of the past atmosphere. How do we know that? In 1957, Charles David Keeling of this institution started measuring atmospheric carbon dioxide reliably for the first time. And the ice core bubble record goes up to about 1995. And so there's a period of overlap between 1957 and 1995 when the two records can be directly compared. And the ice cores agree very, very well with Keeling's record. And so we know that the ice cores are a faithful record of past atmosphere. So this record shows that the carbon dioxide varies between about 200 and 300 parts per million. Today, it's about 400 parts per million. And so this variation is due to the ice ages coming and going. The current levels, the human-caused part of it is this part between about 300 and 400. And this, I should note that this time scale is greatly expanded. This is just the last 150 years, so that you can see just more of the details. If this line was plotted on the same scale as this part of the graph, then it would just be a straight line. It would look just like a straight line going straight up. So humans have changed the atmosphere due to burning fossil fuels, and you see that very clearly in the ice core records. This methane is another important greenhouse gas, and methane has also been changed, almost tripled by human activity. And so there are also these small variations during the ice ages. And temperature is the last graph down below here, and that's showing you essentially the ice ages with fairly rapid ends to the ice ages. So that's one of the things we've learned from studying the ice, one of the stories from the ice. And many of you will have seen this kind of graph before, which is explaining why carbon dioxide and methane cause warming, because the sun's rays go right through the Earth's atmosphere. It's transparent to visible light, but the radiation or energy that leaves the Earth is in the infrared band, and that is absorbed by gases like carbon dioxide and methane, and some of it's re-radiated back to the surface, so it warms the Earth. That's the greenhouse effect. So without any greenhouse gases, without any carbon dioxide or methane in our atmosphere or water vapor, the Earth would be about minus 18 degrees Celsius, about 33 degrees colder than it is today. So in other words, the Earth would be a big ice ball. So we can thank greenhouse gases. Greenhouse gases are our friends, right? But you don't want your friends around all the time, right? Too much friends is not such a good thing. So it's kind of delicately balanced. We need some greenhouse gases, but not too much, okay? So that's why there's a lot of concern about the current burning of fossil fuels, because we're very quickly getting ourselves into some dangerous territory where maybe we have too much of a good thing. Just to give you a feeling for how much warming CO2 causes, this is the pre-industrial concentration of 280. We're about here at 400. And you can see that a doubling from pre-industrial levels will get us up to about here, corresponding to something like 6 degrees Fahrenheit. Most scientists think that we are on the way to a doubling. I tend to agree. We might be very well on the way to a tripling. You can see that that's something like 9 degrees Fahrenheit. But this is global average temperature, and so it doesn't even begin to really tell the full story of how those temperature increases will be distributed across the Earth. They won't be evenly distributed, less over the ocean, more over the land. We tend to live on the land, and so we should probably care more about land temperature increase than global average temperature increase. And this is what it looks like. This is a projection based on the sort of best available physical understanding of the climate system and how carbon dioxide and methane trap heat. And so this is what the temperature is going to look like 100 years from now. And you see that it is heavily concentrated over land, something like 4 to 5 degrees centigrade, which is about 7 to 9 degrees Fahrenheit. And so you see it's concentrated over land and also in the northern hemisphere, not so much over the southern hemisphere. So this is kind of what we're looking at. Now I want to take a little bit of a digression here to talk about one of the things you hear on Fox News. Has anybody listened to Fox News? Yeah. Liberal audience. Yeah. Okay. All right. So anyway, this is one of the things you might hear or read, even in the pages of the esteemed Wall Street Journal, believe it or not. There's a myth that's often repeated, which is that the ice core record shows that carbon dioxide rose after temperature began warming at the ends of ice ages. That is actually true, but the part that's not true is in red. Ergo, carbon dioxide does not cause warming. Well, this is kind of a bunch of assumptions that need to be unpacked here, but in short, there's lots of things besides carbon dioxide that cause climate change. We know that the ice ages were caused by changes in the Earth's orbit. And so the Earth's orbit is essentially what's causing these things to come and go with 100,000 year periodicity. And so this is just the same thing you saw before, but now with CO2 and temperature. So you can see they're actually quite closely correlated, and most of that correlation is because when the ocean warms, it outgasses CO2. So it's mostly because temperature is causing CO2 to change, not the other way around. That's another fact that's often misunderstood. So the fact of it is that the Earth's orbit is acting as the cause, the original cause of the ice ages, and so it's not surprising that temperature starts changing prior to the onset of CO2 rise, but it's actually only a few hundred years. It's not very long. And then together they rise, temperature and CO2 rise together for something like 5,000 years. So it's a very, very small lag compared to the whole change. So the way to think of CO2 in this context is as an amplifier. It's what we call a positive feedback in the sciences. It doesn't mean that it's necessarily a positive thing, but It's an amplifier. That's a better way to say it. And so it really is not a good analog to the situation today. Humans are adding CO2 directly to the atmosphere, and so it's a completely different situation. It's not a good analog. The ice ages are not a good analog for the current situation. If you want to find a good natural analog to the current situation, there actually is one. It happened 55 million years ago when a massive amount of CO2, about 3,000 petagrams, which is, a petagram is a very big number. It's 10 to the 15th grams, but about 3,000 petagrams of carbon were injected into the ocean atmosphere system, kind of just like what's happening today. If humans burned all of the fossil fuels, that would be about 3,000 petagrams. So it's actually a very good analog for what's happening right now. And this event is known as the pale Eocene thermal maximum. And for those of you who are into jargon, but basically it's a very, very good analog for what's going on right now. And indeed, the climate warmed. The global mean temperature warmed about 6 centigrade or 9 Fahrenheit. So in very good agreement with the graph that I showed you there, the sort of best estimates from the physics. And indeed, there were lots of extinctions at the time, but mostly in the deep sea, which is interesting. It seemed that a lot of the sea life could not tolerate the acid from the carbon dioxide, but relatively few extinctions on land. Interesting. Not sure what that means, but it is an analog. So there is an analog. If somebody asks you, well, what does the past climate record actually tell us about this ongoing CO2 injection, that there is an analog. Ice ages are not a good analog, though. So this is the fellow who we really owe the most to in explaining why ice ages happen, Milankovitch. And so during the 1940s, he solved the equations. He mathematically showed that the influence of Jupiter and the moon on the Earth's orbit essentially caused the ice ages and can explain very well what we see in the past record. And so this is what a blow-up looks like of one of those ends of ice ages. So here's the carbon dioxide record chugging along at about 190 parts per million, and then it rises, and this is about the level we had all through the last 10,000 years. So this is about the pre-industrial level. So this rise from here to here took about 5,000 years, and it was about 80 parts per million. And here's the Antarctic temperature, which you see starts rising just a little bit before the carbon dioxide, just a few hundred years. But the driver of it all is this curve here. This is Milankovich's curve, the calculated amount of sunshine that's falling on the Earth during June at 60 degrees north. Why June? Well, it turns out that June is the main melt season on Earth because there's not a whole lot of land in the southern hemisphere, and what land there is in Antarctica is too cold to melt. So the places that really melt are in the northern hemisphere, and it happens in June. And so June sunshine turns out to be the key factor. And you can see that this starts up well before, many thousands of years before carbon dioxide starts rising. And so really the driver of it all is the Earth's orbit, and this shown by this curve right here. Okay, so one way to think about this, if you're talking to a friend who does watch Fox News, is this way. You can think of an analogy. So what you could say is that they do change essentially together, but there's a very small lead. The temperature leads, the CO2 lags. Okay, so what does that mean for causation? Well, think of it in terms of your pocketbook, your finances. Overspending your credit card leads to going into debt, which then leads to interest payments. which leads to more debt. Okay, does that mean that interest does not cause debt? Well, interest certainly lags debt, but how do we know that interest adds to debt? Well, economics says so. We can't explain the data. We can't explain the size of the debt without taking into account interest. Okay, so most people will immediately understand and recognize this. So the analogy is that in the past climate, the orbits are the fundamental cause that causes warming. CO2 rises as a result of the ocean heating up, and then so forth and so on. So this warming effect of CO2 really does raise some questions, because this is CO2 today, and this is kind of where we're headed, business as usual. So you can see that humans are essentially setting out to radically transform the face of the earth. All right, more basic facts. There's a great deal of confusion about the amount of attention that's paid to the past record of climate, say over the past 1,000 years, or even the current temperature, the warming or not warming, or why isn't it warming over the past 15 years and so forth. As far as I'm concerned, this is really kind of a red herring also. The whole case for concern over global warming does not rest on the paleoclimate record or the current measurements of temperature. It rests on basic physics. CO2 traps heat, and plus the undisputed basic measurements like the Keeling curve. We know that humans are adding CO2 to the atmosphere through multiple lines of evidence, most strikingly because fossil fuel CO2 is quite depleted in the rare isotopes of carbon, carbon-13 and carbon-14. And so if the CO2 that's rising right now had a natural cause, you wouldn't see a decline in those isotopes in the atmosphere. In fact, those isotopes are taking a nosedive right now in the atmosphere, consistent with a human fossil fuel source for the CO2. So there's many other lines of evidence, but that's probably the easiest one to explain. So anyway, you have basic physics, you have undisputed measurements, you have a culprit. That's really the major part of the story, and everything else is kind of a distraction, frankly. All right, so I'm going to switch gears now and talk about a few other of the stories that come from the ice about what might happen in our future. This one has a little bit happier in that there's sort of, as you'll see, there's sort of a happy ending that says maybe we can breathe a sigh of relief about this one. One of the things that came out of studying Greenland ice cores over the past 3 decades was that we saw abrupt changes in climate, very, very rapid changes in climate. And a natural question was, could this happen again in the future? And so this is what it looks like standing on a glacier in West Greenland where the old ice comes up to the surface, and you can actually see the difference between younger ice, which is the Holocene, this is the last 10,000 years that we live in, and here's a period called the Younger Dryas, which was right before that, which was very much colder, and it was also dustier, it turns out, and so you can actually see it, and this sharp contact just emphasizes how abrupt that climate change was. Here's what the ice core records actually showed in great detail. The temperature is in green here on this graph, so this is starting out at about minus 31 centigrade at the summit of Greenland. And this is the last 10,000 years, the sort of stable period of climate in which civilization and agriculture developed. So this is sort of think of this as the environment in which our current civilization evolved. So you see these are fairly big climate changes in terms of the effect that they had on humans. This is the so-called medieval warm period when grapes grew in England. You could make wine in England. And here's the Little Ice Age when the ships couldn't reach Iceland because of sea ice and people starved in Iceland. The Vikings abandoned Greenland. So these are climate changes that are known because they impacted humans. Now I'm going to show you the rest of this record, and that's what the climate actually did before humans got into the business of civilization and agriculture. These are big changes. This was about 10 degrees centigrade or 18 degrees Fahrenheit at the summit of Greenland. Probably not so big elsewhere. But clearly the climate is capable of changing radically, and this only happened in about 30 years, and about half of it happened in 1 year. So there's a very, very fast and large climate change. And so the natural question is, could this happen again? The cause of it is not really known, but the leading hypothesis, let's say, is that the North Atlantic drift, which is this current here shown in red at the surface, was interrupted, and then when it restarted, it caused that abrupt warming. This current today keeps the temperature of places like Norway and Northern Europe quite a bit warmer than it would otherwise be in the winter, because the salt and heat that's brought in by this current tends to discourage sea ice from forming over the ocean. That water cools, and because cold water is dense, it sinks to the bottom, and this blue ribbon here is meant to show the cold, salty, dense water flowing south in the interior of the ocean. So this circulation is more or less continuous, with warm water being drawn up from the subtropics, cooling off, sinking, and flowing back south. That's what we call the meridional overturning circulation. And it plays a very important role, actually, today in keeping the North Atlantic Ocean ice-free in winter. And the reason is simple. It's just that fresh water is less dense, and so all else being equal, it will tend to accumulate and then form a layer of fresh water on top of the salt water. And that, in turn, makes it easy for sea ice to form. The reason is that if you don't have that layer of fresh water, you have to cool down the whole ocean column, all 3,000 meters of it. And there's just not enough time in a season to extract all that heat from 3,000 meters of water. So essentially the sea ice just never forms. But when you make a layer of fresh water, it's only 100 meters thick or so, and it's very easy to extract the heat from that 100-meter thick layer. And so basically these layers of fresh water make it possible to form sea ice in winter. Well, then the climate really notices that, because once you have sea ice on top of the ocean, as far as the atmosphere is concerned, that's just like land. And so the sea ice is a very effective insulator, keeps the ocean heat from getting out into the atmosphere. And so the North Atlantic probably becomes like Siberia in winter, and the atmosphere reacts accordingly. So this is all very interesting, because we know that north of about 40 degrees latitude, the rainfall exceeds evaporation, and so all else being equal, fresh water will accumulate unless the ocean continually brings in a supply of salt, as it does today. And the ocean current, interestingly, is kept healthy by the salt, because the salt water is necessary to keep the water dense so it can sink to the bottom and then pull more water in. So that's what a positive feedback, as we say. So another feedback, and that's makes it potentially susceptible to interruption. So a lot of scientists got worried about 20 years ago that global warming would add more fresh water into the high latitude ocean and would discourage this sinking of salty dense water and slow down the whole circulation. So that was a big worry. And I think the good news is that it turns out that because of the warming of the planet, not only is the rainfall increasing, but the evaporation is also increasing. Evaporation just took about 30 years to catch up with the freshwater transport in the atmosphere. So now the North Atlantic Ocean is getting saltier. So it looks like this is going to be a stable situation. Interestingly enough, the Atlantic as a whole is getting saltier right now, and the Pacific is getting fresher. And the explanation seems to be that as the planet warms, the air can hold more water vapor, and the Atlantic naturally loses water vapor to the Pacific because you have winds blowing across the Isthmus of Panama that are tropical. They carry an enormous amount of water vapor. And nothing like that exists on the eastern side of the Atlantic. So, good news is this overturning circulation is probably safe in our future, so we're probably not going to have abrupt climate changes again. The other thing to consider is that the magnitude of those abrupt climate changes was certainly accentuated by the presence of lots and lots of sea ice in the past. And in the future world, it's going to be so warm that there just won't be a whole lot of sea ice. And so in that sense, the severity of those abrupt climate changes is quite unlikely to be reproduced in the future. So that's why I say it's sort of good news. I don't think we're going to have abrupt climate change in the future. So one of the other worries was that methane that's trapped in an ice-like substance called hydrate, methane hydrate, might become destabilized in a warming world because it's only stable at temperatures of below about 4 degrees C. And as the climate warms, this methane ice-like substance could become turning into a gas. It could become destabilized. And so one of the big questions was, what happened during these previous abrupt warming events that we know happened? I said that at the summit of Greenland, it was 10 degrees centigrade or 18 degrees Fahrenheit warming in just a few decades. A very, very large and rapid warming, faster than what's happening today. So we reasoned that if those methane hydrates were susceptible to being destabilized and allowing methane to come out into the atmosphere and cause more greenhouse warming, it should have happened at the end of the Younger Dryas. It should have happened then because the warming was so big and so much bigger than what's happening today. So we thought, how do we test whether that happened or not? Well, it turns out that the clathrate or methane hydrate carbon has no carbon-14. Carbon-14 is a radioactive isotope with a half-life of about 5,000 years. And so since these hydrates, many of them are millions of years old, they don't have any carbon-14. It's all decayed away by radioactive decay. Whereas other forms of methane, say mostly coming from tropical wetlands, those forms of methane do have carbon-14. So you can use carbon-14 to discriminate between the two sources of methane to the atmosphere. And so we set out to measure the carbon-14 content of ancient methane as it was just before and just after that big rapid warming. And here's our chamber for melting down a ton of ice. It turns out it takes about a ton of ice to measure carbon-14 because of the fact that it's so rare. Carbon-14, very rare molecule. And so we also went to an Antarctic site. This is a place called Taylor Glacier in Antarctica. So this is drilling in Taylor Glacier with big samples, and this is our vacuum chamber with big ice cores, big fat ice cores. It takes about a ton of ice to actually get a single number of carbon-14 in atmospheric methane. And so here we are filling this up, and that's just further evidence that it's not all about work. You got to have some fun too. And so anyway, the good news that I want to leave you with to sort of close on a happy note is that we found that the carbon-14 content of atmospheric methane did not change at all across that huge warming event, even though the concentration of methane increased by 50%. So the implication is that the methane hydrates were stable during that major warming that happened. And so the implication is that future warming will probably not cause a burst of methane to come out into the atmosphere. In fact, if you look at what's happening today, most of the methane hydrate that's currently decomposing due to the recent warming never makes it to the atmosphere. The methane is released, and before it travels 10 or 20 centimeters, it's gobbled up by a class of microorganisms that eat methane. They make their living by oxidizing methane if there's any oxygen in the soil. So probably what happened to all that methane in the past was that it got converted to carbon dioxide. So yes, it does add carbon dioxide, but methane is 200 times more potent molecule for molecule than carbon dioxide. So the effect of adding that amount of carbon dioxide is not very significant compared to the worries about methane. So that's a little piece of good news that I hope I can leave you with, and I'd be delighted to answer any questions. Thank you. Great question. So the question is, was the little ice age in the medieval warm period also caused by some kind of oscillation of the Earth's axis or orbital dynamics? The answer is no, actually. Current evidence suggests that it was caused by a combination of the sun, the output of the sun actually increasing in the medieval warm period and decreasing during the little ice age. And the reason we believe this is that indirect proxies for the strength of the solar magnetic field showed that the magnetic field was very strong, indicating a high output of solar energy during the medieval warm period, and contrarily low output during the little ice age. And also probably volcanoes. Volcanoes tend to cool the climate. There was an unusual burst of volcanism at the beginning of the little ice age that probably kicked the system into a different mode. Yeah. So the question is, there are some other factors that have cooling influence, such as sulfate aerosols, and have we been measuring those in the ice cores? Yes, we have. So it's very interesting. The anthropogenic revolution is quite evident in the sulfur content of Greenland ice cores. You see basically all the coal burning, because coal tends to have a lot of sulfur in it. You see all the coal burning that started around 1850 in the northern hemisphere in the concentration of sulfur in the Greenland ice core. And you also see things like lead from leaded gasoline, and the good news there is that the lead content of Greenland snow has gone way down in the last 30 years due to the elimination of leaded gasoline. So that's an environmental success story. Yeah, the question is about how long after the snow falls does it get compressed enough that it actually seals the gases in. It's usually about 200 years today. In Greenland, it's up to 5,000 years in some places in Antarctica where it's very dry and it only snows about 2 centimeters a year. So it's quite variable. Yeah, and that's one of the big challenges in our field, is to figure out what the difference is in age between the gas and the ice. Okay, so the question was, did you say that methane is not a big problem? And I'm confused about that because I read that methane is a big problem. And so the answer is, I was only talking about methane hydrate. Methane has lots of other sources: landfills, leaking natural gas pipelines, fracking, cows, termites, you name it. There's lots and lots of sources of methane. I did not mean to imply that those are not a problem. Quite the contrary. You know, as I said, that methane has almost tripled under human influence, and that is no doubt in part to those things that I just mentioned. You know, probably mostly cows and landfills, but yeah, all those things are important for explaining that tripling of methane.
Worry about methane still.
Absolutely, yeah, absolutely. I just was trying to talk about methane hydrate, which is a specific class of, you know, kind of methane, yeah. Oh, okay, so if I can sort of paraphrase, you know, quantitatively, how do the methane hydrates compare to the other sources of fossil fuel? Did I get that right? Yeah, so methane hydrates are currently not exploited as a fuel at all. Part of the problem is that they're disseminated. They're little blebs of methane hydrate that are disseminated at fairly low concentration through enormous volumes of seafloor sediment. And so it's not very practical at the present time, even though the Japanese are experimenting with this. It's just not economic at the present time to use methane hydrate as an energy source. The concerns that I talked about were from this disseminated methane being warmed by the ongoing warming that's happening right now, okay? So not having anything to do with economic harvesting of methane hydrate. You see the difference there. As far as the total amount of methane hydrate, it is enormous. It's thought to be at least several times the total inventory of all coal, oil, and natural gas combined. So that it potentially an enormous reservoir of hydrocarbon fuel. The problem is that it's disseminated, so it's not easy to get out, and nobody's figured out a way to make it flow nicely the way oil flows so that you can concentrate it. But anyway, does that answer your question? Yeah. So the question is, why exactly did I say that we're unlikely to experience an abrupt, rapid climate change again? And the answer is that the interruption of that North Atlantic circulation seems to require a lot of sea ice and circumstances that increase the freshness of the North Atlantic. And right now, we're going exactly the opposite direction. We're going towards a world that has much less sea ice, and we're also getting saltier. The Atlantic is getting saltier. So both of those factors militate against an interruption of this overturning circulation in the Atlantic. And in order to get the abrupt warming, first you have to turn off the circulation and then turn it back on again. So that's, it's the turning back on that seems to cause that abrupt warming. Does that help?
Yes, it does.
Yeah, okay. Yeah, so the question is, what is the oldest ice that I've ever worked with, and is it harder to read the information in the bubbles? 800,000 years is about as old as the ice core record goes back, and as far as we can tell, it's not any different than ice that formed yesterday. So we're lucky in that sense. It seems to be well preserved. The only thing that's a little more difficult is that it tends to be squashed very thin down at the bottom of a glacier, and so the ice is very has very thin layers. The layers start out maybe 10 centimeters thick, and they get squished all the way down to less than a millimeter. So it's harder to count annual layers in ice that's that old, but most everything else seems to be okay.
Well, thank you very much, Jeff, for a great presentation.